Welcome to Mathematical Finance. Today, we are diving into the absolute bedrock of the financial world, measuring interest rates. Whether you are pricing a simple loan or a complex billion-dollar derivative, understanding exactly how money grows over time is the first step. We will explore how different compounding frequencies change the value of money and why advanced mathematics relies on a concept called continuous compounding. Let us get started and see how money truly multiplies. Now that we know what we are studying, let us look at how compounding actually works. Imagine rolling a small snowball down a long, snowy hill. As it rolls, it picks up fresh snow, making it larger. Because it is larger, its surface area increases, allowing it to pick up even more snow on the next rotation. This is exactly how compound interest works with money. If you stop the snowball once a year to pack the snow tightly, that is like annual discrete compounding. But if you let it roll smoothly without ever stopping, picking up snow continuously at every microscopic fraction of a second, that is continuous compounding. In finance, how often we stop to pack the snow changes everything. Building on that snowball analogy, let us look at the mathematical formula for discrete compounding. This formula tells us exactly how much money we will have if the bank only pays us at set times, like monthly or annually. The formula is A equals P times 1 plus R over M, all raised to the power of M times N. Here P is your starting principal. R is the annual interest rate. The variable M is crucial. It is the compounding frequency, or how many times per year interest is added. Finally, N is the number of years. If you increase the frequency M, the final amount A also increases because you start earning interest on your interest sooner. This discrete formula we just saw leads us to an important question. What happens if we compound faster and faster? In everyday banking, interest might be compounded monthly or daily. However, in mathematical finance, we almost exclusively use continuous compounding. We do this by taking the discrete formula and pushing it to its absolute mathematical limit. We imagine the compounding frequency approaching infinity. This means we are calculating and adding interest an infinite number of times per year, at every possible instant. We prefer this continuous measurement because it creates a smooth, unbroken mathematical curve. This smooth flow makes the complex calculus used in pricing options and derivatives much easier to solve. Now that we understand the concept of infinite compounding, let us see its mathematical form. By applying standard calculus rules for limits involving infinity, the complex discrete expression simplifies into this beautiful and elegant exponential function. A equals P times e to the power of r into n. This is the absolute bedrock of mathematical finance. The symbol E represents Euler's number, a fundamental mathematical constant approximately equal to 2.71828. The other variables remain the same. P is the principal, R is the continuous rate, and N is the time in years. Because E is greater than 1, the final amount grows exponentially as either the rate or the time increases. This allows us to model money as a smooth, continuous process. Before we move on to calculations, let us see this difference visually. Look at the graph on your screen. The horizontal axis represents time in years, and the vertical axis represents the accumulated value of your money. The blue staircase line shows discrete annual compounding. Notice how the value stays flat and only jumps at specific yearly intervals. Now look at the smooth red curve representing continuous compounding. It hugs the top of these steps, representing the absolute maximum growth possible for a given rate. The smooth nature of this continuous red curve is exactly why calculus can be applied to it so easily, and why financial engineers prefer it over the jagged discrete steps. Now that we have seen the formulas and the graph, let us apply them to a concrete example. Suppose a struggling student invests a small savings of $100 into a bank account offering a 10% annual interest rate for exactly 1 year. We want to know how much more money they would make with continuous compounding instead of annual compounding. First, we set up the discrete formula. We plug in our principal of 100, our rate of 0.10, and a frequency of 1 since it is annual. Evaluating the fraction inside the parenthesis gives 1.10. Multiplying this by 100 yields exactly $110. So with annual compounding, the student has $110 at the end of the year. Continuing with our student's investment, let us now calculate the continuous compounding result to see the difference. We substitute the exact same principal of 100, rate of 0.10, and time of 1 year into a continuous formula involving Euler's number. The exponent is simply 0.10 times 1. Evaluating e to the power of 0.10 gives approximately 1.110517. Multiplying this decimal by our $100 principal yields $110.52. Comparing the two results, we see that continuous compounding earns the student an extra 52 cents over the course of the year. While 52 cents seems small for a $100 investment, on a $1 billion institutional trade, this difference becomes massive. So we have seen how continuous compounding generates slightly more money. This brings us to a practical problem. In the real world, a bank might quote an interest rate that is compounded semi-annually or quarterly. But a financial engineer needs a continuously compounded rate to plug into advanced pricing models. Therefore, we must know how to translate a rate measured with a discrete frequency into an equivalent continuously compounded rate. The golden rule here is that two rates are considered equivalent if they produce the exact same final amount of money after the exact same amount of time, starting with the same principal. This ensures apples-to-apples comparisons across the market. To solve this translation problem, we use a specific conversion formula. This formula allows us to convert a discretely compounded rate, R sub m, into a continuously compounded rate, R sub c. The formula states that R sub c equals m multiplied by the natural logarithm of 1 plus R sub m over m. Here, the symbol ln stands for the natural logarithm, which is the inverse mathematical operation of the exponential function e. By plugging in the discrete rate and the compounding frequency m, we can find the exact continuous rate that would yield the same amount of money. As the continuous rate increases, the equivalent discrete rate must also increase to keep pace. Let us put this conversion formula to work with a real-world scenario. Suppose a corporate bond pays an interest rate of 8% per year, compounded quarterly. A financial engineer wants to use this bond's rate in the Black-Scholes pricing model, which strictly requires continuously compounded rates. We need to find the equivalent continuous rate. We are given a discrete rate of 0.08 and a compounding frequency of 4, because quarterly means 4 times a year. We plug these values into our natural logarithm conversion formula. First, we divide 0.08 by 4, which gives 0.02. This means the bond pays 2% interest every single quarter. Continuing our calculation, we add the 0.02 to 1 to get a growth factor of 1.02 for a single quarter. Next, we apply the natural logarithm to this growth factor. Using a calculator, the natural log of 1.02 evaluates to approximately 0.019802. This decimal represents the continuous rate equivalent for just one single quarter. To find the annualized rate, we multiply this result by 4. Multiplying by 4 gives a final continuously compounded rate of 0.0792 or 7.92%. This means a continuous rate of 7.92% generates the exact same money as a quarterly rate of 8%. The engineer can now safely plug this into their model. Now that we have successfully used this conversion formula, let us understand where it comes from. We derive it by setting the continuous growth formula on the left equal to the discrete growth formula on the right. Because we are looking for equivalent rates, the starting principal P and the number of years N are the exact same on both sides. This means we can mathematically cancel out the principal P. Then, by taking the nth root of both sides, we eliminate the variable n entirely. This leaves us with a simplified equation stating that the growth factor for 1 year of continuous compounding is exactly equal to the growth factor for 1 year of discrete compounding. Continuing from our simplified equation, our goal is to isolate the continuous rate, R sub c. Right now, it is trapped in the exponent above the base e. To bring it down, we need to remove that exponential base. We do this by taking the natural logarithm of both sides, because the natural log and the exponential function cancel each other out. Applying the logarithm brings the exponent down, and by logarithm rules, the exponent m on the right side moves to the front. This gives us our final derived formula. We have proven exactly how to translate any discrete rate into a continuous one, ensuring our mathematical models always reflect reality accurately. We have covered a lot of ground today, so let us reinforce the most important ideas. First, measuring interest rates is all about defining the compounding frequency. How often interest is calculated and added to your balance? Second, while real-world banks use discrete frequencies like monthly or annually, mathematical finance relies on continuous compounding for its mathematical elegance and smooth curves. Finally, by using simple logarithmic and exponential formulas, we can easily translate any real-world discrete rate into a continuous rate suitable for advanced financial modeling. Mastering this concept unlocks the door to understanding all future topics in derivative pricing. Great job following along.